If you fell into a black hole, the scariest part might not be dying. It might be that, from far away, you never quite seem to finish falling. You fade, you redden, your clock slows down, and to everyone watching, you're basically frozen at the edge of forever. But from your point of view, you cross a line in space where the rest of the universe can still see out, but you can't get back. And after that, physics stops being polite. Let's make this concrete. A black hole isn't a cosmic vacuum cleaner roaming around space, sucking up everything nearby. If the sun magically became a black hole with the same mass, Earth wouldn't spiral in. We'd keep orbiting because gravity at our distance would be the same. The nightmare begins only if you get close enough, where gravity gets so intense that every possible path forward points inward. The boundary is called the event horizon. That name sounds technical, but the idea is brutal. It's the point where escape becomes impossible. Not hard, not expensive. Impossible. You could fire the most powerful rocket ever built. You could shine a flashlight straight outward. Once you're inside, even light can't climb out, and since nothing can outrun light, no message, no scream, no selfie, no last-minute apology can escape either. Now, what you actually experience depends hugely on the black hole's size. Fall toward a small black hole, something with a few times the mass of the sun, and things get nasty early. Gravity doesn't just pull on you, it pulls harder on the parts of you closer to the black hole. Your feet, if they're pointed downward, feel more gravity than your head. That difference is tidal force. On Earth, tides raise oceans. Near a small black hole, tides stretch you like warm cheese and squeeze you from the sides. Scientists call it spaghettification, which is somehow both silly and horrifying. Around a stellar mass black hole, you might be torn apart before you even reach the event horizon. The closer you get, the more the difference in gravity across your body grows. Your bones, your organs, your atoms don't get to vote. You're stretched into a long, thin stream of matter. It's not a clean movie death. It's the universe using gravity like a pasta machine. But here's the twist. If the black hole is supermassive, like the monster sitting in the center of our galaxy, the event horizon can be enormous, millions of kilometers across. In that case, the tidal forces at the horizon might be gentle enough that you wouldn't feel anything special as you crossed it. No glowing wall, no cosmic toll booth, no sign saying congratulations, you've made a terrible decision. Locally for a while, you'd just be floating. That's because the event horizon isn't a physical surface. It's more like a point of no return drawn by the geometry of space-time. If you're falling freely, you might pass through it without noticing the exact moment. Your watch keeps ticking. Your heart keeps beating, at least briefly. Your spaceship instruments might not flash red at the boundary itself. The weirdness isn't that the horizon burns you. The weirdness is that after crossing it, every direction that counts as the future leads deeper in. To understand that, imagine trying to walk north on Earth. Most places you can choose north, south, east, or west. But once you're at the North Pole, every direction you step is south. Inside a black hole, something similar happens with time and space. Outside, moving inward is a direction you can fight. Inside, inward becomes as unavoidable as tomorrow. You don't fall toward the center the way a rock falls toward the ground. You move toward the center the way you move toward next Tuesday. Meanwhile, if someone far away watches you fall, they see a completely different story. As you approach the event horizon, your light has to fight harder and harder to escape. It loses energy, stretching toward redder wavelengths. You look dimmer, your movements appear slower, your clock seems to crawl. From their perspective, you never quite cross. You fade into darkness, smeared across time, like the universe is buffering and never finishes the download. But that's only what they see from far away. You don't feel frozen. You don't watch the outside universe speed up infinitely in some magical montage. You cross, and whatever light can still reach you from outside may look distorted and shifted, but your personal time continues normally. This is one of the strangest lessons from relativity. Different observers can disagree about time and still both be right. Before you even get that far, though, there's a practical problem. Real black holes are often messy. If there's gas, dust, stars, or unlucky planets nearby, that material can form an accretion disk, a screaming hot whirlpool of plasma spiraling around the hole. Friction and magnetic fields heat it to absurd temperatures. It can blast out X-rays and jets powerful enough to ruin your day from a very safe distance. So if you're falling into an active black hole, the black hole itself might not get first dibs. The neighborhood could cook you, shred you, or irradiate you before the horizon enters the conversation. Let's pretend you picked a quiet, supermassive black hole with no raging disk, and you fall in wearing the best imaginary spacesuit money can buy. You cross the horizon alive. For a short time, you might still look around. Light from outside can still fall in after you, so the universe isn't instantly gone. But you can't send anything back. Communication becomes one way. You're receiving the last mail delivery from reality, with no return address. Then the tidal forces grow. Even in a huge black hole, gentle doesn't last. As you move deeper, the difference in gravity across your body ramps up. Your feet and head no longer agree about where they're going. The stretching returns. The squeezing returns. Eventually, biology loses. Then chemistry loses. Then atoms lose their familiar structure. Whatever used to be, you get forced into an extreme future we can't fully describe. Classical general relativity says everything inside keeps heading toward the singularity, a place where density becomes infinite and the math blows up. But physicists don't think infinity is a satisfying physical answer. Usually, infinity means our theory has hit its limit. General relativity is incredible at describing gravity on large scales. Quantum physics is incredible at describing tiny scales. Inside a black hole, you need both at once, and we don't yet have the final theory that tells us exactly what happens at the deepest point. So does the singularity really exist? Maybe not in the simple way textbooks draw it. It might be replaced by some quantum gravitational state we don't understand yet. The honest answer is that no one knows. That's not a failure of imagination. It's a real frontier. Black holes are where our best maps overlap, distort, and leave a blank spot labeled "Figure this out." There's another puzzle hiding here. What happens to information? In physics, information means the details needed to describe a system. If you burn a book, the words seem gone, but in principle, the smoke, heat, ash, and light still carry traces of what happened. Black holes make that idea uncomfortable. If things fall in, and the black hole later slowly evaporates through Hawking radiation, does the information come back out somehow? Is it scrambled on the horizon? Is it stored in a way that makes space itself act like a hologram? This is still one of the biggest arguments in theoretical physics. For you personally, though, the outcome isn't ambiguous in any useful sense. You don't survive. You don't pop out into another universe with a funny travel story. Wormholes are allowed in some equations, but that doesn't mean nature builds stable, passable tunnels for astronauts. The realistic answer is harsher and cleaner. Crossing the event horizon traps your future, and the rising tidal forces destroy you. The timing depends on the black hole. A small one kills you fast, likely before the horizon. A supermassive one might let you cross without drama, then gives you a limited fall time before the end. For the black hole at the center of the Milky Way, that could be minutes to hours depending on the path. Not enough for a grand tour. Enough maybe to realize that the event horizon wasn't the monster. The monster was the geometry waiting underneath. And that's what makes black holes so fascinating. They aren't just objects in space. They're places where space and time trade roles, where escape isn't a matter of speed, and where the universe forces us to admit our theories aren't finished. Falling into one would be the worst experiment ever performed, but thinking through it teaches us something profound. Reality doesn't have to be intuitive to be consistent. So if someone asks what happens when you fall into a black hole, here's the short version. From far away, you slow down, redden, and fade at the edge. From your own perspective, you keep falling through a point of no return. Around a small black hole, you're stretched apart before you get there. Around a giant quiet one, you might cross peacefully, but only for a while. After that, every future points inward, and the final answer waits in the part of physics we're still trying to understand. Black holes are terrifying because they don't break the rules. They reveal what the rules were saying all along, and if that made your brain bend a little, that's the right reaction. Subscribe for more trips to the edge of what we know, preferably from a much safer distance.